Today, I'm going to talk about the paper Protean VM Allocation Service at Scale. This is the joint work between Microsoft Azure and Microsoft Research. My name is Abhisek, and I work as a software engineer in Azure. Protean is the core virtual machine allocation service in Azure. This is the service that allocates millions of VMs onto millions of servers every single day. A single instance of Protean manages all allocations for an entire availability zone, which, as of today, can host more than 100,000 machines. Needless to say, Protean is one of those core platform services that are absolutely critical for Azure's operation. This paper covers two different themes. On one hand, it provides a comprehensive account of a real-world resource allocation service used by a large cloud provider. On the other hand, it describes a few new and interesting techniques that we have developed along the way. So in this talk, I will touch upon both of these themes a little bit. Let me start by discussing the scale, diversity, and unpredictability that we see in Azure. These pose some interesting challenges for Protean. Here in Microsoft, we like to refer to Azure as the world's computer. And truly, the scale at which it operates today is staggering. Its footprint covers 61 regions and hundreds of edge sites. In a single day, more than 5 million new VMs are created over 2 million servers. These millions of servers across the globe are organized in a hierarchy. At the top is the region, which consists of a set of data centers and can have up to 3 availability zones. An availability zone has its independent power, cooling, and networking installations and can host more than 100,000 machines. Regions and zones are exposed to customers directly. The zone, in turn, is divided into many clusters. Now, unlike a zone, machines in a cluster are homogeneous. They have identical configurations and capabilities, a fact that we use to optimize the allocation service performance. More on that later. A zone can host many different kinds of machines. In the last 20 years or so, we have already used 8 generations of hardware, and it is perfectly possible that a zone hosts 4 or 5 of them at the same time. Aside from general purpose hardware, we also have specialized computing substrates. For example, machines with large memories, accelerators with high-performance interconnects, etc. The placement algorithms, of course, heavily depend on the underlying hardware. So this variety adds a lot of complexity. Applications that run on this hardware are also very diverse. At the top level, Azure provides numerous services to its customers, starting from a single VM to large sets of VMs with auto-scaling, and even more sophisticated offerings such as databases and machine learning services. All these applications ultimately consume hardware resources through VMs. To Protean, all resource requests are presented through groups of VMs. Internally, we call these groups tenants. A single tenant can have 1 VM or more than 1,000 VMs. VMs within a tenant can express certain relationships among each other, such as fault domains, depending on the top-level applications that are creating them. Protean is responsible for placing each of these VMs on the machines in the inventory. A VM is ultimately the unit of resource allocation. Resources required by a VM are defined through the VM's type or size. Today, we have over 700 types of VMs, and it's growing. We can see some examples here. The red speck on the left needs 1 core and 2 gigabytes of memory. Monster on the right needs 224 cores and 12 terabytes. So there is a lot of variation among these types, not just in their absolute requirements, but also in the ratio of cores to memory, for example. Newer types are sometimes not supported in older generations. That creates its own challenges. VMs can differ in many other aspects as well, for example, priority or fault domain requirements. VMs have dozens of such traits that influence placement decisions. Here, we see the distribution of allocated VMs by their type in a couple of our zones. If we look at the chart on the left, we can see a large number of VM types in each zone, but a few of them are a lot more popular than others. On the right, we see the distribution by allocated cores. Most VMs use 1 to 4 cores, but some VMs are large enough to consume entire machines. This variation in VM types and distributions makes it very hard to pack these VMs well. Another interesting aspect is the variation in demand. These charts here show the rate of incoming requests for one of our busier zones. If we look at requests per hour at the left, we see some diurnal patterns. However, if we zoom in a bit and look at requests per second on the right, we see a lot of spikes. Now, these spikes are large and hard to predict. Ideally, Protean should be able to handle the spikes without any degradation of service. Protean has to achieve many objectives. First and foremost, Protean should make correct assignments of VMs to machines, honoring every customer constraint. But beyond that, we also have some internal objectives that are very important, and Protean tries to achieve those as best as it can. For example, excellent customer experience is extremely important. To that end, Protean prefers machines that can start VMs sooner. It considers potential disruptions from future hardware maintenance events while placing VMs on machines. It tries to minimize eviction of low priority VMs. Almost as important is low fragmentation. At Azure scale, even 1% reduction in fragmentation can lead to $100 million in savings per year. Good packing also leaves more machines empty. Empty machines are really important for us. They help us in finding space for large, hard-to-place VMs. There are a few objectives that are actually about Protean itself. Extensibility and adaptability. It should be easy and safe to add new behavior or alternatively tune existing behavior in Protean. Then there is interpretability. A very common question that we have to answer is, why did my allocation fail? So it is important to provide detailed reasons for allocation failures. To summarize then, the hardware is diverse, the requests vary widely and can be hard to predict, the objectives are many. Protean has to make correct, high-quality placement decisions and in a way that is robust and understandable. Let us see how it achieves all of that. It starts by expressing the complex allocation logic through a series of rules. Allocating a VM is essentially about selecting the best machine or node for that VM from all the machines in the inventory. Protean does this in 2 steps. First, a filtering step. Rejects all nodes that can't be used for this VM. In other words, this step enforces all the hard constraints, and it does that through a series of validator rules. Second, the remaining nodes are then sorted using a series of preference rules, which express the soft constraints. We should note here that the sorting is strictly hierarchical. So any rule can only break ties among nodes that are considered equal by the rule above it. We have over 100 such rules in production today. Now, let us look at these rules in a little more detail. Validator rules enforce hard constraints. Each validator rule implements the isValid method, which basically determines if a node or a cluster is valid for a VM request. For example, the RNodeResourcesValid rule checks if a node has enough resources to fit a VM. Preference rules, on the other hand, express soft constraints. Each preference rule implements the compare method, which is used to compare 2 nodes to determine which one is more suitable for a new VM. Here is an example. prefer non-empty machines. It prefers partially full nodes over completely empty nodes for placing a VM. Because, as I mentioned before, having more empty nodes is a good thing for us. An interesting question here is how to handle multiple preference rules effectively. Since we are using a strict hierarchical sorting, if a rule prefers a single node over all other nodes, then all the weaker rules become pointless. So we pay a lot of attention to prevent rules from becoming too stringent. Such rules are usually smoothened through quantization. A good example is the best fit rule. This is an important rule that implements a multidimensional best fit algorithm to improve packing. This rule gives a normalized score to every machine, which can take any value between 0 and 1. This score is quantized into some buckets to smoothen the rule. The table here shows the effect of choosing different bucket counts. The second column shows packing density, which is a measure of how well the nodes are packed. The third column shows the percent of nodes that the rule places in its top bucket. The lower this is, the more stringent the rule is. As we see, as the number of buckets go up, the packing density improves, but the gains diminish, especially after a bucket count of 3. At the same time, the rule places fewer and fewer nodes in the top bucket. This rule-based approach really helps in adding new behaviors easily. Also makes diagnosing allocation failures quite straightforward. Now, I'm going to briefly touch upon the techniques we use to maintain good throughput and latency at scale. Protean needs to increase its throughput as the size of the zone increases. To do that, it employs multiple allocation agents. The number of agents can be increased as demand and inventory size go up. These agents operate concurrently using an optimistic concurrency model. This is exactly the same framework that was introduced by Google's Omega. However, we have had to develop some interesting conflict detection and reduction techniques. You can find more details about this in the paper. Our goal here is to keep VM allocation times low as the inventory grows. We have a couple of techniques for this. First, we use a cheap filter and sort step to pre-select eligible and high-quality clusters. It is a lot cheaper to reason in clusters than in machines because the number of clusters are much lower than the number of machines. Then, the machine selection step operates just on the nodes in the selected clusters. This is really the bottleneck step. So we use a multi-layered caching framework to expedite this part. Our caching optimizations are motivated by a couple of observations. First, the requests exhibit temporal locality. Requests are similar to each other even across all the different traits that they might have. Second, inventory changes slowly. A zone might have over 100,000 machines, but the number of machines that change their state between two allocations are much lower. So the core idea here is this. When we evaluate a VM request, we get a sorted list of valid nodes. We want to store and reuse that list. When the next request arrives, we just want to update the list by re-evaluating the positions of the nodes that have changed in the meantime. That is the only computation we want to do. Let me explain this idea a bit more using a simple example. Here is the baseline implementation of the R-node resources valid rule that I had mentioned before. As you can see, it is calling the R-node resources valid method inside the isValid method. So this method will be executed for every node, every VM request. And this method might require a lot of computation. So that is not good. Also notice that the rule depends on a single request trait, the VM type. So an improvement here would be to use a lookup table instead. As we see, the table has two keys, the VM type and the node. Now, isValid is a constant time operation. This way, we can create a single rule object and keep reusing it for every request. So now the question is, how do we populate that table? To that end, each rule implements an update method. This method is called immediately before the rule object is used, with the list of machines that were modified from the last time it was called. The paper describes how this list is computed efficiently, but I'm not going into that here. Now, we can clearly see that the heavy computation is done only inside the update method, only for the modified nodes. Can we improve this further? Notice that a single rule object is storing the state for every VM type, hence the less nested loop in the update method. But this is kind of inefficient. Instead, we can split this one object into multiple objects, one for every VM type. Now, each of these objects compute and store the state for a single VM type only. Hence, no more nested loops in the update method. When a request arrives, the object for the corresponding VM type is first updated and then used in evaluation. This technique allows us to take advantage of the request locality that I had mentioned earlier. But we can go further. We can actually store and reuse the entire evaluation result, the ordered list of machines. We store them in these rule evaluation objects. Alongside, we have to store the rules that were used to compute this evaluation result. And all the trade values that are used by these rules taken together identify these evaluation objects. In the toy example here, we have two traits, x and y. X can have values x1 and x2. Y can have values y1 and y2. We also have two rules. R1 depends on both x and y. R2 depends on x. In this setup, there are 4 unique combinations of trade values. Correspondingly, we can have 4 different rule evaluation objects and 4 different R1 objects. Since R2 depends on just x, only 2 objects are created for it, each of which is shared between the 2 evaluation objects. So you can see how each evaluation object forms the root of a dependency tree. Like this, a hierarchy of dependent objects are created and cached in constant-sized LRU pools. Since I've been focusing on the caching techniques in this talk, I wanted to end with some results about the impact of these techniques in production. The chart on the left shows how cache hits improve allocation times. We see an order of magnitude improvement if we can use cached results while performing an allocation. The chart on the right is about the memory overhead of maintaining these cached objects. Thankfully, the overhead scales sublinearly with inventory size, and at current zone sizes, this overhead is not really an issue. So this brings us to the end of this talk. There are a lot more interesting details and results in the paper. Please check it out. As part of this paper, we are releasing some production traces that can be used to explore different packing algorithms. Also, I wanted to take a moment to acknowledge the contributions of the rest of the members of the team that owns this service. Thank you very much.